Okay, so that's recording.
Okay.
Okay, so 2 times the magnification.
Right.
It's on bright field.
Yes.
Quite a slow. It's quite a viscous material. This metal box.
Yeah,
So it's 40% constant, and so you can see the materials kind of move quite in interesting ways, right?
Yeah. Does that change over time? Because some of that is probably mixing.
Yeah, yeah. But the behaviour of the things are quite peculiar.
Well, I made a chart on.
So if you go into depth light,
dark field one.
yeah, essentially this is how you increase the frequency of the reaction.
Hang on. So this, what sort of light are we putting in?
It's UVA 357.
Okay. Yeah.
So essentially the shape of the molecules is such that the coordination of purity carbonyl onto the ion allows the transfer of energy to photons to reduce.
Why is it going from left to right?
Because of probably where we're getting.
Centering?
No, I think it's maybe due to. I think it's using external features as well, light sources, to drive the reaction. Or it might be where the centre of the the bubble is. Yeah, right. So.
Yeah, no, I just wanted to.
Yeah.
Okay.
So it's the centre point where it's attracted to.
Yeah.
And so you can move into read and see things that are in a different way. And that's at 1% action. And see timings.
Well, collapsing bubbles are another way of getting a bit of energy.
Yeah, cavitation effects.
Definitely.
Definitely. The interesting thing is you can change your periodicity of what your refresh rate.
Are those bubbles collapsing on the liquid?
Because
they won't be in focus at the top.
No, that's the thing. They're actually, you can change your focal point.
Yeah.
And therefore see what's happening there.
Yeah, you're not far above the base of this.
No.
Above the.
No, so you have a kind of spatial resolution.
So that is a cavitation event.
Yeah.
The spherical, so there could be a bit of energy there. From that.
Yeah.
The other things I'm having trouble. Well, I don't know about the energetics of what you've described earlier.
Yeah.
But certainly the bubble might.
So now you can actually start seeing some ghosting effects. And this is essentially slowing. It's like going past a picket fence and seeing a car and the wheels actually end up going backwards because of the strobing effect.
Right.
So the frequency of the screen and the frequency of the refresh rate capture give you a strobing effect, essentially slowing time down.
Right.
But we're looking down through magnification, so we're actually going ahead in time, but then slowing it down.
Right.
And so you can do weird and wonderful things at the end of the day when you increase your
bubble following over.
these things are pretty weird stuff afoot.
Mhm. Lots of
Yeah, I'll show this tool as well. It'll be interesting to see that we still get a lot of the reaction going on. So I think external photons as well, because UVA is found in the shadows, right?
Yeah.
So I think part of it's the actual external light sources interfering.
Right.
What are these? Electrons. That's what I reckon it is. These are like particles that spontaneously come into existence.
Well, they could.
Or you can't see them because it's spatial-temporal relationship, isn't?
I'll tell you what.
Yeah.
Like that bubble chamber.
A bubble chamber.
Well, we'll test that.
Yeah.
I have a very regular source here. Not very powerful, it's just a small one.
Yeah, I got out a Geiger counter and I tried testing to see if Geiger, if emissions were coming up. I couldn't pick up anything above background,
Yeah.
but I've got it upstairs if you need it.
No, I don't think it's that way, because that's what you may well have as background.
Mm.
You put that near your sample
Yeah.
and just see if anything changes. That's lead on the back,
Okay.
that's the source.
Okay.
It's Emerson 241 microcurie, so it's claimed to be safe.
You can see here, look at this.
Yeah.
There's a phosphorescence.
So that should be emitting about 10,000 particles per second. So
Right.
withdraw it now and just see if the field changes. Let's go back.
There's a change there. There's a shadow imaging happening. Right?
Yeah.
So you can see here's the, look at this.
Yeah.
Take that away,
Oh,
it takes it away.
Yeah, that's
That's
just
the
a
reflection. Yeah, but that's giving you an image analysis, right?
Yeah.
Here are the images.
Mhm.
And if we change our focal point, here we they're the crystals.
Right. You just try again. Yeah, I don't think it's a problem. It might be, but I don't think that's in essence. That's when the raw energy out of the source.
Hmm.
Yeah, okay.
But doing that kind of strobing and slowing things down allows you to kind of see it. That particular. Right here. So I've got this as well happening on this line.
We're looking above it or below it?
Below it.
On the lower face? Because that could
Yeah.
just be wrong.
Yeah, could be.
Just fingerprints and that type of thing.
Right. But the periodicity and stuff like that is
Yeah.
a bit weird, right?
Yeah. You sometimes see that in optics when they're comparing the optics. Could also be on the condenser as well.
Mm. What?
You can prove that by taking the slide down. industry focus and stuff.
Yeah. So we need to get higher now.
Not very well ordered those Christmas,
No.
some of them, but they seem to be growing layers.
So you can essentially certainly if I just flick on the light again, I think the light is actually part of the story.
Right.
And what should that do? Should that go tick, if that's, you should hear it? Or are you looking just for a difference?
I'm just looking for a
Mm.
could also influence you to stick this slightly as well.
Mm.
Although it shouldn't be, it's not very penetrating. So how long does this process go for before it reaches equilibrium? Or is it a system that's stimulated by
That is stimulated by the
light?
photons.
So
Yeah.
it's in equilibrium in a sense.
Yeah. So,
Yeah.
so essentially you need the coordination of the ion onto the material, and then you need to tune to the right frequency for it to catalyze, photocatalyze.
Right, so it's just slightly the difference, that bubble should collapse, is that what you're saying?
Yeah, well, eventually. Depends on how much hydrogen peroxide's around.
Yeah. Question is what? Does it collapse because it leaves the seam? Or does it collapse
It
because...
grows from the same position again and again.
Yeah.
Yeah.
But that collapsing bubble is not just a bubble quickly leaving the seam, is it?
It's very hard to tell, right?
Yeah, I mean, doing
Yeah. But there's other weird stuff going on. There appear to be things, okay, there could be just crystals flying around because of the cavitation of the band.
Well, that's gravity motion essentially.
Yeah.
Question is that a whole bubble or a half a bubble?
So you hit it with a gap heat in minutes. And it's the DAPI line, right? UVA. Bang, bang.
You see, the bubble could disappear if it was growing off the surface as a hemisphere.
Yeah.
When it leaves the surface, it becomes a sphere, which is a negative lens. So it might instantly disappear for that reason.
Right.
Plus also it's leaving the seam.
Yeah.
So, well, it won't disappear if it forms a sphere, but the point is it's gone bubble. Yeah, certainly.
Often with an edge, right? You have a lensing effect associated with an edge.
Right.
And see how things are bouncing. So there's a and when you hit it with So that could just be evaporation off the surface, but the ones that go like that,
Yes.
there's obviously a current going on. And then,
So that's the edge of, is that the edge of a drop then?
yeah, the droplet. Yeah. And then weird things can go on, like you can then focus your energy into.
It is possible that your detector
Yeah.
could detect background radiation. Where's the detector? It's in here.
Yeah, yeah.
Okay. I mean, there may well be a few counts from the detector because of them coming, configuration things.
Right.
Certainly, if you take a normal video camera and put the source near it, you do see counts.
Okay. So you can just use video
Yeah.
directly pointed here and capture that incident light that's coming out of the. Is it?
Well, no, what I'm saying is if
Yeah.
I take the source and put it near the camera, you get a few speckles in the image.
Right.
So it's a low quality X-ray detector.
Yeah. So you can see kind of a shadowing and
Yeah.
so shadow imaging.
Mm. Well, that's a Schmear
So that's from
yeah.
the light that's. So that wasn't that dense previously.
Mm.
So it's kind of.
Take the slide away from it. And just refocus because you need to most sort of see what if the just go through a range of focus. Okay, not an issue. Okay, it's on the slide. Well,
You can see it on this coloured material.
yeah. Sorry,
No. You see, it's not exactly difficult to create.
yeah. Six slides, so never looked at this microscope some years ago when we were great, but
Yeah, it's
always a general.
Yeah. It's very easy to use. So you get, obviously, if you have a bubble, right, you have a lens. Here it is.
Yeah.
The shape inside of it is essentially this shape here. So you can see my fingers. So it's obviously taking light from around. So how many photons are you actually capturing when you're doing something?
Well, what you need to make is a box.
It has one,
Yeah.
but essentially I'm interested in the fact that I've got multiple, it's responding to multiple light sources,
Right.
and therefore, you can do stuff by essentially.
You had a very bad fluorescent light that could do 253.7, but it's unlikely.
I don't think, that one's got too much energy, right?
There's another one at 435, which you will see.
Okay.
and probably another one around the 3,000 as well.
Yep.
Certainly 3,000. Probably 3,000. I don't think you'd see that over through the journals with that. The fourth or five eight was something.
So you can actually see now, right, you wobble it. There's a connected cohesiveness to the material,
Yeah.
right? So it's weird, right? I put inorganic things here. I've been doing lensing with bubbles, Fenton chemistry, and I'm making stuff.
Yeah.
Right? So this is regenerative medicine essentially, and this is precursors to life.
Right.
That's my understanding, and I'm trying to get the crux of what's the wavelength spectrum profile being generated. Because if you do so there's essentially a membranous material which is very hard to see, but that's it. You can shake it and make it move.
Yeah. So I wonder if the bubbles are leaving fossils behind. You know, they grow and
Seeds.
yeah. That's
The response is like it's about 750 milliseconds for the visual.
yeah, you can see it just displacing very slightly with your fingers, which might be a ball of some sort. And it's displacing it slightly.
Yeah. And the fact that it's got a lot of light and QDOT, so it's absorbing light at 445
Right.
and emitting it between 525 and 800.
Yeah.
So it's taking energy from the light, right? The frequency is changing, so it's taking energy from it.
In my past research, I've been inclined to stick a microphone on this light and listen to it.
How would I do that?
I'm not too sure. Probably
Because I want to use
probably
sound
the
frequencies.
electric detector.
Yeah, okay.
And then you modulate it and
Tune to the
it
frequencies.
tells you what's being absorbed by the material.
Yeah.
And the sound will be louder.
Well, I'm wondering whether the solid slide is doing anything as well, right?
Well,
Am I?
are you dissolving the slide?
Wow, that's what I'm wondering.
We should have a close look at the slide when you clean it off.
Yeah, yeah,
It's possible you're doing that.
yeah. Fenton chemistry breaks most things down.
There are some fairly gloopy silicates you can bring up.
Well, what's giving that, right?
Yeah.
There's a interlaced mesh
Yes.
generated after the chemistry, and I added more hydrogen peroxide and very little reaction.
Well, it may not be membranes, it might be threads due to
Yeah.
one particle contacting another, and you're making sort of like a spider web.
Yeah. There is the spider web.
Can you do polymers on that?
Phase contrast.
Well, maybe polymers on there. It's probably not thick enough for the
Yeah.
chaos or something. what that would do is if you had membranes of the right thickness running and they came it up,
Yeah.
you might get a response.
But, when I've taken a corn kernel and essentially used Dippy and long pass
Right.
and growing the germination process. So, obviously light is triggering growth, but it's triggering this chemistry,
Yes.
which is triggering the growth.
Yes.
Yeah. So all I'm doing is tuning into the natural chemistry or the frequencies that animals and plants are using to regenerate. And
So
grow.
what's that frequency?
That's 445.
Okay.
So that's NADPH, NADH.
Yeah, well, it's 4358 out there. So
Right. No.
And it's been broadened by the phosphate, of course.
Yeah.
But when
So I might be getting 2 photons at the same wavelength.
you may be.
Because this is plus or minus. Because my idea is E equals MC squared, right? C squared is C times C. It's 2 photons.
I mean, a fluorescent light, you've got something that crudely looks like a black body, but it's not.
Yeah.
And then you've got the spectral line superimposed on it. The 435 is just quite strong.
Okay. Just looking. Yeah, so for DEPI, its excitation is 357 plus or minus 44, and emissions 447 plus or minus
Yes.
60. So essentially this translates to that as an emission wavelength, and that's an absorption wavelength. So you kind of get this walking down of frequencies based on going essentially down an electron transport system. Yeah. Yeah, I've got some grow lights if you really want. I've got a variety of LEDs.
It's modulating. You wouldn't see it by turning it on and off.
No, you have to
Maybe it's make a candle.
get the right position.
Yeah.
So it's responding to light, right?
Yes.
It's like it's alive.
Yeah.
The beginnings of life. It's weird. It is weird.
Yeah.
I know it's weird, but that's there's just so much weird stuff going on that I only know what I see,
Yes.
and so I spend my time watching and looking and seeing how it's behaving, and I know I'm influencing it based on what I'm doing.
The other thing is, if you put would this combination of liquids actually grow stuff?
That's an interesting question, right? So this is what's found in Manuka honey, and it produces
Superoxide.
Yeah, superoxide.
Yeah.
Yeah. So I know it produces superoxide. Superoxide can react with, iron to do, and then methyl glycol is actually going in a reverse direction through to lactic acid, pyruvate, and so you've got the glycolysis cycle kind of running in reverse via methyl glycol and glycosylase system.
Well, yeah, what I'm leading up to is I might could be inclined to sterilise the materials in the slide.
Yeah.
So now
And see if I can grow something.
see if the behave the same.
Yeah. If I'm getting other life entering into that. Adding to
you're not
that.
helping.
No. But when I'm dealing with biological systems, they're inherently disgusting, right? They're just completely dirty, and that's what I'm dealing with. I'm dealing with biologically complex materials, and want to bust them up to create these precursor molecules, and I'm getting other things being generated in the process.
Yeah.
Yeah.
Well, do you want me to set my...
Yeah, I'll just move this another way. I think it's worthwhile having a look.
Yeah.
There's some interesting things going on. I know there is. So the other thing I have is a form of heme iron, which has come out of meat industry.
Right.
And so essentially it's black gold. It's iron 2 collated into hemoglobin, or no, not hemoglobin, but the heme prosthetic root, so it absorbs light.
Right.
And yeah, it does the same thing, right? It does meat in chemistry.
Okay.
Yeah. They make this by the ton.
That's kind of like dry blood, is it?
Yeah, pretty much. They steam coagulate it, or they precipitate it. The other thing that you might suggest is, why is it that the intensity or the rate of reaction increases dramatically, going from 2 times magnification to 10 times magnification? Is it because I'm actually focusing the light in a
We're
small
going
area?
through the same means.
Yeah.
That's the reason why.
Right, so I'm actually increasing my EV value
Yeah.
by 10 times.
Well,
By 5 times, going from 2 to 5.
yeah.
So if I'm at 3.7 at 357, then I'm going up to about 2 times that. So I'm actually at 7.4.
Oh, you've got a beam like that
Yeah.
through a lens.
Yeah.
Lens is the same.
Yeah.
But no, the lens is different.
So I can change my
So
point. So I've got an alpha and a mega
Yeah.
starter.
until you reach the numerical aperture of your system when you slide on that,
Yeah.
in which case it will reflect.
Right.
So you have a certain numerical aperture you can get in there,
Yeah.
which is usually less than 1.
Mm.
And if you use all immersion, you can take it up to somewhere.
Well, I think the bubbles themselves do that, right? They,
Well, they can.
they're an internal.
Well, what they could do, a bubble could do